we are, all right. All right, hi everybody, and welcome to the first or kickoff of the September 2020 nationwide live stream star party with the Fred Lawrence Whipple Observatory, the Feynman Observatory, and the NASA JPL Solar System Ambassador Program. And we're so excited that you guys can join us this evening and really be a part of what we're bringing to the community. So for those of you who don't know, typically we've done this event in person, and we are so excited to tell you that now that we're virtual, we can expand our program and involve scientists from every corner of the Smithsonian Astrophysical Observatory, Harvard Observatory, and the Center for Astrophysics. So just a couple of announcements for those of you who are local to Arizona. First, I have to report to you that the observatory remains closed. There's a few of you who've seen the inside of my office, so you know I'm in here because you recognize the purple wall. But we remain closed to the public during this time as we continue to build new exhibits and to keep you safe while we're figuring out the best way to reopen the observatory. We're definitely going to be doing that soon. And if you haven't taken our public survey yet on exhibits and programming, I encourage you to go ahead and take that survey. You can access it via our website at cfa.harvard.edu/FLWO, or you can access it through our Facebook page. We post it every week, so you'll be able to see it there. And tonight, I'm especially excited to welcome up-and-coming theoretical astrophysicist Amir Siraj. And something that excites me so much about Amir is the theories that he has proposed for astrophysics and the way that it changes how we see astrophysics and the way that science is being directed. So very recently, Amir has been featured repeatedly in Forbes, Gizmodo, and even overseas on Times Radio and in other publications, other major publications, even the New York Times. Tonight, Amir is going to be speaking to us about a recent theory about the sun's early life and how it may have had a solar binary companion. So one other thing I wanted to mention to you about Amir is that he's also a classically trained pianist and is training at the New England Conservatory. If you haven't seen it already, I encourage you to get on Facebook and check out Music for the Parks and listen to some of his amazing music. So without further ado, I'm going to turn everything over to Amir. And then after this presentation, you'll have a brief Q&A period, and then we'll move on to Brian Cummins of Chantilly, Virginia, showing us some objects in the night. We finally got him here and fully connected. So I'm excited to see Brian over there. And then we'll also have Daniel Cervantes from the Feynman Observatory in Indiana. So we'll be seeing quite some interesting things tonight that are a little bit different depending on where you live. So without further ado, please welcome Amir Siraj.
Thank you for the warm introduction, Amy, and thank you all for being here tonight. One moment, just sharing my screen. Perfect. So my name is Amir Siraj. I am a theoretical astrophysicist and student at Harvard University, and I am delighted to be here with you this evening. Tonight, I'll be discussing a really fascinating question that my advisor, Professor Avi Loeb, and I stumbled upon. And I'll walk you through our scientific process, and I'll also touch on some of the incredible facets of our solar system along the way. So the story begins with the outer solar system. It's very hard to study because of how distant the outer solar system is. But since the outer solar system is less sheltered by the gravitational potential of the sun, it can carry really interesting and often surprising information about the history of the solar system. So the title of my talk today is "Was the Sun Born a Twin?" And I'll sort of build up to that. But I'm fascinated by the peculiarities of the outer solar system, as I was just discussing, and one of these involves the Oort cloud. Now, the Oort cloud is a vast collection of icy bodies that spans thousands to hundreds of thousands times the distance between the Earth and the Sun. And unlike the rest of the solar system, which is shaped in a disk, the Oort cloud is shaped in a sphere. To give you a sense of perspective, if Alpha Centauri, which is the nearest star, and other neighboring stars had Oort clouds, they would be touching like interlocked billiard balls, filling the entirety of space. The inner edge of the Oort cloud is set by scattering from the planets, and the outer edge of the Oort cloud is set by the galactic tide. The Oort cloud is the reservoir, the source of these beautiful long period comets that we all know so well. And these are injected in the solar system by passing stars and by fluctuations of the galactic tide. In addition, the Oort cloud may have played an influential role in shaping Earth's history, from potentially delivering water to possibly causing mass extinctions like that of the dinosaurs. Because the Oort cloud is so immense and distant, it's very difficult to study directly. So instead, the most successful approach has been to study the orbital and physical characteristics of long period comets, and to match these observations to a distribution of objects in the outer solar system that would give rise to the long period comets. As a result, astronomers have been able to set constraints on the size and the shape of the Oort cloud. Simultaneously, theorists like myself have been trying to come up with formation models that could explain how the Oort cloud formed as observed. And to be quite honest, this has proved very challenging. In particular, models have encountered considerable difficulty in matching the observed ratio of objects between the outermost and innermost parts of the Oort cloud. This is true of the previously leading model, which proposed that the Oort cloud formed from the planetesimals that were scattered as a result of planetary migration in the solar system as the planets were finding their places. And the model fails to explain really why there are so many objects in the Oort cloud. So this is one of the great mysteries that has fascinated me. The other is Planet Nine. So Planet Nine is a proposed but not yet discovered planet. And the existence of Planet Nine was first thought up in 2016. And the reason it was proposed was to explain some peculiar orbits in the outer solar system, some of them shown here. In particular, this is a class of objects called trans-Neptunian objects, or TNOs. And there were very interesting asymmetries in the distribution of these objects. And these are simply solar system bodies that cross the orbit of Neptune. So they're very far out and very difficult to study. But these asymmetries supported the idea that an unseen planet lurking more than 10 times further from the sun than Neptune, with a mass of 5 to 10 times the mass of the Earth, might actually be the best explanation for producing the observed orbits of these TNOs. So the search for Planet Nine has been on ever since, and it will be greatly aided by the Vera Rubin Observatory in Chile, which is expected to deliver the verdict on Planet Nine's existence, and it's coming online soon. It will also evaluate alternative models, such as a Planet 9 black hole, something that I've worked on, a potentially massive belt of planetesimals, or the possibility that the observed asymmetries in TNOs are merely a statistical fluke. But if it exists, one of the central issues with Planet 9 will be explaining its origin. So to date, there have been 3 leading origin scenarios. One is in situ formation, 2 is scattering, and 3 is capture. So the first, in situ formation, posits that Planet 9 formed at its current location, about 500 times the distance between the Earth and the Sun. And while this may sound like a very nice and parsimonious explanation, the original disk of material from which the planets formed was likely truncated much closer to the orbit of Neptune, which would make it nearly impossible to amass enough material to build a planet so massive at the distance of Planet 9. So the second possibility is scattering. If Planet 9 formed amongst the giant planets, Jupiter, Saturn, Uranus, and Neptune, it could have been gravitationally kicked into a more distant orbit, at which point the influence of passing stars would have circularized Planet 9's orbit. The flaw in this model is that it takes quite a bit of fine-tuning to get such an orbit. And in fact, it's quite unlikely that such a kick would result in Planet 9 remaining in the solar system. An ejection from the solar system would actually be much more probable. The third scenario is capture. So either stealing Planet 9 from a passing planetary system, or adopting one of the myriad free-floating planets that were ejected from their parent systems during the chaotic early periods of planetary system formation. The issue with a capture scenario is, again, the likelihood of such an event occurring. You need a planet at just the right distance and just the right relative velocity in order to have a favorable chance at capture. Now, the Sun spent its first 100 million years or so of its life in the solar birth cluster, which was a much denser stellar environment than the one we live in today. The birth cluster formed from the cloud of gas that produced the Sun and its many siblings, and it consisted of a rich collection of stars and gas. The high stellar density in the birth cluster means a high density of free-floating planetesimals, which were the byproducts of planetary system formation, improving the odds of capturing Planet 9 relative to the likelihood in the field where we are today. However, papers have shown that even with the advantage afforded by the density of the birth cluster, the likelihood of capture is only perhaps a few percent, which is comparable to the other origin scenarios, and quite frankly, not a very favorable number. So we have these 2 great puzzles in the outer solar system. How did the Oort cloud form as observed? And if Planet 9 exists, how did it originate? So these questions have been in the back of my mind for a while. And in addition to being a scientist, as Amy mentioned, I'm also a classical musician, a pianist as well. And I would say one of the advantages of this era of social distancing from a personal standpoint has been that I've been able to spend a great deal of time alone playing music and thinking about science. And one day I found myself playing a really wonderful fugue by Johann Sebastian Bach. And a fugue is a form of music that relies on the interrelation between several distinct voices that mirror and also play off of each other. And part of the fugue was a duet between two voices in which they almost seemed to be revolving around one another. This reminded me of the dance that the two stars in a binary star system perform as they circle their common center of mass. Now, this got me thinking more about stellar binaries, which are extremely common in the galaxy. In fact, more than half of sun-like stars were born in binary systems. In particular, I was considering one of the very special properties of binary systems, which is the fact that they have enormous capture cross sections. This means that they are far more efficient at gravitationally trapping unbound objects than a lone star, like a large fishing net in space. What I realized was that a large capture cross-section, this fishing net, could potentially help solve both the formation of the Oort cloud and the origin of Planet 9. And that was a really exciting moment. And as I dug into both the physical and statistical details, it became more and more clear that a temporary, equal mass binary companion to the sun was not only plausible, but could actually be a considerably favorable model for both capturing Planet 9 and for forming the Oort cloud. So the obvious question is this even possible? And really that comes down to a couple of underlying questions. One is, would the stability of the solar system be affected? And the other is, could there already be other observable signatures that could confirm or deny the previous existence of such a companion? Regarding the first question, the question of stability, the primary issue here would be the survival of Planet 9 itself, because if it exists, Planet 9 would be by far the most distant planet from the sun. And turns out that an equal mass companion at a distance of 3 times that of Planet 9 ensures that Planet 9 would not be ejected. So that's good news. And in terms of the other known planets, the ones that we know so well, the orbits would have been unaffected by what's called Kozai-Lydov oscillations from such a companion. And this is because the tidal force, which causes these oscillations, scales with the cube of distance. So our solar system is stable, but actually this discussion of tidal torque induced by the binary system is interesting, because we actually observe a 6-degree tilt in the sun's spin axis relative to the plane of the ecliptic where the planets are, which is surprising, but which has actually been proposed to potentially arise from close encounters with other stars in the birth cluster, and which most certainly could also be explained with this temporary companion. In terms of other observational signatures, it might include, for instance, if the binary companion was never ejected, it would be an unmistakably bright point of light in the sky, about as bright as the half-illuminated moon, a second sun. And of course, we don't see that. But this raises actually a very good scientific question, which is ejection of the binary companion probable? Or is it weird that we don't see one today if one existed in the past? It turns out that at the distance considered, there is at least a 50% chance that a passing star in the birth cluster would have ripped the binary apart, which is good news for the binary model. And of course, while the minimum impact parameter of a stellar encounter, impact parameter being distance relative to the sun, is similar between the cluster and the field where we are today. In the birth cluster, the stars moved much slower relative to each other. And so this makes the kicks much more potent. And this implies that the companion star was almost certainly lost while the sun was still in the birth cluster. And finally, I would be remiss not to mention the various lines of evidence over the years of anomalies in the orbital distribution of long period comets, which have been proposed to be indicative of a current Jupiter mass solar companion in the Oort cloud, which was ruled out. But these effects could potentially be consistent with a twin star that was lost. Now, in terms of how we quantified the expected abundance of outer Oort cloud objects in our model, we used the number density of interstellar comets calibrated by the interstellar comet 2I Borisov and scaled to the number density in the birth cluster. And we took the capture cross-section of the binary combined with the lifetime of the solar birth cluster to get the total number of captured objects in the Oort cloud. We then considered how many objects in the Oort cloud would be lost during the encounter with a passing star that tears the binary apart. And we found that only about 1% of captured outer Oort cloud objects would survive. We then considered effects of other passing stars throughout the sun's lifetime and their potentially erosive effects on the Oort cloud. And our final estimate for the number of objects in the Oort cloud turned out to be in excellent agreement with observations, much to our surprise, having an overlapping coefficient about 5 times greater than the previously leading model. We went through a similar process with Planet 9 and found that since a binary would increase the capture cross-section by about a factor of 20, relative to a lone star, this would bring the chance that Planet 9 was captured from a few percent up to near unity. So considering the big picture from a statistical point of view, from the chance that the sun started out in this particular configuration to the likelihood of losing the companion star, and also taking into account the improvement in explaining the origins of the outer Oort cloud and Planet 9, a discovery of a captured Planet 9 would lead to our binary model being favored over the lone stellar history that has been long assumed by 90% to 10%, which is very exciting. And the specific smoking gun for this model that will really tell us that this was likely a binary will be a significant overabundance of dwarf planets, so similar to Pluto here or Sedna. And these dwarf planets would have similar orbits to Planet 9. And why would these dwarf planets exist? The same reason as Planet 9 would be captured, which is the greatly expanded capture cross-section that is afforded by a stellar binary system. This will be observable by the upcoming Vera Rubin Observatory, which is expected, again, to begin operations soon. So, yes, our sun may have very well been a twin, and hopefully within a few years we'll be able to understand the sun's early history in more breathtaking detail and with increased certainty. So thank you everyone for listening, and I'm happy to take any questions you might have.
Thank you so much, Amir. This is amazing. We actually have quite a long list of questions for you. So our first three questions all come from Bob in Green Valley, Arizona. So I'll start with his first question, which is, what would Planet Nine's mass have to be for all of this to happen as theorized?
That's a great question. Thank you, Bob. So the mass of Planet Nine would have to be between 5 and 10 times the mass of the Earth, and so that is pretty much consistent with what has been estimated previously.
Excellent. Thank you so much. So we've got another question from Bob, which is, assume Planet Nine were found. So say that the viewer Ruben turns on and immediately finds Planet Nine. How long would it be before we could get a probe to Planet Nine?
That's an excellent question. So Planet Nine is thought to be at a distance of around 500 times that between the Earth and the Sun. And right now the furthest man-made object from Earth the furthest man-made objects from Earth are the Voyager probes, and those are to order of magnitude about 100 times the distance between the Earth and the Sun. They're not at 200 yet, so it will take a long time. It will take a lifetime to get to Planet Nine with conventional rocket technologies. And so that's why it's so important to invest and come up with new propulsion technology. So one that is, very exciting and could potentially send a probe to Planet Nine is what's called a light sail. And this is kind of exactly what it sounds like, which is a sail. Instead of being pushed by the wind, it would be pushed by light, because light carries a little bit of momentum. And if you shine enough light, you can actually build up quite a, remarkable acceleration. So if we send a very, let's say a few grams, a giant sail out in space and build a huge array of lasers on Earth and shine that laser array to this light sail, we could potentially accelerate it up to 20% of the speed of light, and that would allow us to get to Planet Nine very quickly. And this is, what some companies and organizations such as the Breakthrough Starshot Initiative are currently pursuing.
Wonderful. So I have some follow-up questions to that, but I'll ask them at another time. We'll keep going with our guests' questions. So the Bob again has asked, with trillions of Oort cloud objects, why don't we see an occasional eclipse of a star? It seems as if that would be going on all the time.
Another excellent question. So such a eclipse of a star caused by a small body is called a stellar occultation. And we actually do see stellar occultations by objects in the Kuiper belt and the Oort cloud. And it's actually an excellent way of discovering small Oort cloud objects. And I've actually written about proposing stellar occultations as a way to discover small interstellar objects. And in fact, the Center for Astrophysics is involved in a stellar occultation survey. Director Charles Alcock is one of the investigators on TAOS, which is the Taiwanese American Occultation Survey. And they've done a lot of incredible work in terms of, finding objects that are so small and so distant that they could not be discovered using any other current technology.
Great. Okay, so we've got our next question comes from Stephen Brown, who I'll give a shout out to. Stephen is one of our volunteers at the Whipple Observatory, and despite our shutdown, has remained completely dedicated and helping, with these types of presentations and with other projects that we're doing, the renovation project that we're doing. So thank you so much, Stephen, for that. And his question is, from the observations of the orbit disturbances of the solar bodies, can the orbital period of Planet 9 be calculated?
Yeah, so right now the current range of distances that Planet 9 could exist at are about 400 to 800 astronomical units, and using Kepler's law, you can just take the semi-major axis in astronomical units and raise it to the 3/2 power, and that's the orbital period of Planet 9. So as you can imagine, it is quite long, and it is a frozen world if it exists. But nevertheless, it will be very exciting to study. And it's like my advisor Avi once said, it's like finding something in your own backyard that you didn't even know about. So it's really, really exciting.
He does. I love that analogy that Avi has for us about finding hidden things in your own backyard. I think the last time he described it, he said it would be like finding a relative living in your backyard and you never knew they were there.
Exactly.
I've really enjoyed that myself. Our next question comes from Stacy Kissel. In addition to the question already asked about the period, the orbital period, do you have any idea what the eccentricity of that orbital period would be, or of that orbit would be?
Yeah, so I just have to give a brief shout out because Stacy Kissel, Miss Kissel, was my physics teacher in high school, and she was actually the physics teacher that actually sparked my interest in physics. I was generally interested in science beforehand, but Miss Kissel was actually the reason that I got into physics and ended up getting into astrophysics. So I'm forever indebted to Miss Kissel for showing me the beauty of physics. And right, so in terms of Planet 9's eccentricity, it is somewhat constrained. I believe the current range is about 0.2 to 0.5. So, it's certainly not like Earth's orbit or these really nice circular, completely or nearly completely circular orbits in the inner solar system. Although, then again, it's not totally, it's not near hyperbolic. And the reason for that sort of like in between nature is, whether it was captured or whether it was scattered, it would have, come in with a pretty high eccentricity, probably closer to hyperbolic than not. And but then over the ensuing billions of years, because of the distance, Planet 9 would be at hundreds of astronomical units. It would actually interact with the passing stars on a pretty regular basis, and these passing stars would serve to circularize the orbit of Planet 9. And so it's probably low to mid eccentricity state. But again, that'll be a really interesting thing to look at if Planet 9 is discovered, and that will certainly give us hints as to how it formed. So thanks, Ms. Kissel, for that question.
And I'll just say thank you so much, Ms. Kissel, for everything that you do and all of the students that you inspire to continue in science. It's so important to have wonderful teachers early on in education to inspire people like Amir to continue on in the study of science and in STEM fields. Thank you so much, because I get to work with him now on a regular basis, which is a really big joy for me as well. Our next question, Amir, comes again from Stephen Brown, our volunteer. So are you saying that if we had a binary system that we lost one of them, could they have instead combined? Which is a really interesting question, of course, given Warren Brown's research. So
yes. Yeah, no, that's a really interesting question. So I guess there's sort of two types of binary systems, speaking broadly. One is close binaries and the other is wide binaries, and they have different names, but essentially what they mean is the period is short versus the period is long. And so the sun would have been in a wide binary system, because if it was involved in a close or tight binary system, we would either still see the binary companion today, or we might not be around to see it, or as you mentioned, if two stars are orbiting in a very tight configuration, it is possible for them to spiral into each other and collide. But this, thankfully, that did not happen, and this binary companion, if the sun had it, would have been at a distance of about 1,500 astronomical units. So this is a pretty wide, it's not the widest binary out there, but it is would be classified as a wide binary, and so there wouldn't really be a chance of spiraling inwards. The only risk would be losing the binary companion. But that's a great question. Thanks, Stephen.
Thank you so much for that. As a follow-up to that, I think Bob has asked another question, Bob from Green Valley. Could the sun's companion be proved by its composition through spectroscopy?
This is another really interesting question that I've thought about myself. And so, as I mentioned, the birth cluster, the solar birth cluster, was formed from a cloud of gas, and that cloud of gas was sort of led to the existence of many, many stars, not just the sun and not just its potential binary companion, but many other siblings and cousins. And so, and actually, a couple of stars have been identified as having somewhat similar chemical compositions and masses to the sun. And these could certainly be solar siblings in terms of, existing and coming from the solar birth cluster. But all of there's no reason why the binary companion that was gravitationally bound to the sun would have a special chemical signature. So all of these stars would actually be expected to have similar compositions. And, the one sort of downside here is that, aside from not being able to assess and find the long lost twin using spectroscopy, the other thing is that because so much time has passed since the dispersal of the solar birth cluster, the stars have now been scattered throughout the Milky Way galaxy. And so there's really also no way to know in terms of location where a solar birth twin might be located. It could quite literally be anywhere in the galaxy.
Excellent, great. So we've got one last question for you, Amir, here, which is, have people estimated the potential for life on Planet Nine? So this goes back to the type of world that it is, and any type of life, right? So of course, we together know something that we can't really talk about, with some of Avi's new research coming out, so careful on that front. But then the second half of that question, it looks like we'll have another question after this. So let me repeat the question, having given the forewarning about the embargoed research. Have people estimated for the potential of life on Planet Nine, even if outside of the Goldilocks zone?
Mm-hmm. Yeah, no, that's a really interesting point. So, habitable planets are typically, or the habitable zone is really, just means where liquid water can exist. And so that's how scientists use the term. And, that's how a lot of searches are directed for habitable planets or Earth-like planets. We're looking for planets at distances from their stars at which liquid water could be sustained. So really just between 0 degrees centigrade and 100 degrees centigrade. And the reason for that is because that's the only we only have a sample size of one for life, and for planets that support life, and water is actually quite a remarkable chemical, and it does all sorts of things. It acts as a universal solvent, and it really does wonders, and it seems essential for life. But there's other sources of heat and sources of energy. So what I would say is that the habitable zone is not the exclusive, source of energy for life, because all life needs energy. There has been research that was published. Yes, this has definitely been published, so I can talk about it, by by Professor Avi Loeb and Professor Manasvi Lingam. And one possibility, they've done an incredible scope of work in astrobiology, really pioneering the field. But one example that I'll give is the idea that planets, certain planets might have been formed with an overabundance of radioactive elements, and if a planet had a very radioactive core, you can imagine that could be a source of heat. So even if the planet was, at the distance of planet 9, or the planet wouldn't even need to be bound to a star. It could be a free floating planet, but if it had an internal source of heat, such as these, radioactive isotopes, there would be no need for a star. And so that is certainly a possibility, but there are many others. And all I would say is that, it's great to be thinking in this way, because I think it's really easy to get caught up in conventions, and the habitable zone is just a convention. That's all that it is.
Thank you so much for that. I know that's always a little bit difficult. So for everyone out there to understand the sort of overarching conversation that happened there, sometimes research is ongoing within the Center for Astrophysics. And so we think very carefully about how we answer questions so that we don't accidentally scoop research that we're working on. So things that we are currently learning about but haven't yet announced to the public. So for our colleagues out there who just had the Venus phosphine announcement in the last few days, that was a very long-term project for them that was tightly under wraps and very quiet and difficult to not talk about for a very long time. So we all struggle with that. So Amir, we have just this one last question for you, and everyone out there, thank you so much. This is the last question we're going to take, because we do have some astronomers out there in the dark and what I'm sure is cold in Virginia, waiting for us. So the last question comes from Stephen Brown. Do we have any estimate of how long ago we lost the binary companion, the sun's twin?
Right. So the binary companion would have been lost while the sun was still in its birth cluster. And the birth cluster lasted for about 100 million years. And while that may sound like a long time, to put in perspective, the age of the solar system is, of order 4.5 billion years. And the age of the universe is about 14 billion years. So 100 million years is 2% of the lifetime of the solar system, and even less of the lifetime of the universe. And so the sun, if it had a binary companion, it would have been lost within that 100 million year timescale.
All right, great. Well, Amir, thank you so much for all of your wonderful answers and for your amazing presentation. I think that I can speak for all of the audience members and for our astronomers out there. I see Brian in the dark, barely lit, like a candle, like he's lit by a candle from underneath, waiting to show off objects. We've got clear skies tonight, by the way, everyone on the East Coast. But Amir, thank you again so much. I'm so excited to see where your career is going to go and how things are going to continue to progress. And I'm also so excited to see where Music for the Parks is going to head, and to see how that continues to grow as well. So thank you so much for joining us. You're welcome to stick around and watch the telescopes work.
Thank you. Thank you so much for having me, Amy. And I'm very, very excited to see the sky through Brian and Daniel's eyes.
All right, great. Thank you so much. So we're going to, everyone, we're going to move on now to Brian Cummins in Chantilly, Virginia, with our first object of the evening.
All right. Hey, everybody. Can you hear me okay, Amy?
I can. Sorry, I had already muted myself, but I can hear you great.
All right, outstanding, great. Hey, everybody, my name is Brian Cummins. I'm an amateur astronomer from Chantilly, Virginia. I'm set up right now in Sky Meadows State Park, which is about a little over an hour outside of Washington, D.C. So I'm a member of the Northern Virginia Astronomy Club, NOVAC.com. And so we do public nights, and we have, it's actually a very large organization, scope loaner programs, all kinds of cool stuff. So if you're in the area, go to our website and look for opportunities to come out and see through our telescopes live, not just over video. I'm also a member of the JPL NASA Solar System Ambassadors, where we do outreach to the community, and this is one of those examples. So very happy to be here. So I thought maybe I'd start with, I guess I should share my screen first, apologies. Okay, so assuming you can see that. If you can't, Amy, just jump in, but I'll assume that you can. So I was setting up tonight, and this park, it's a state park, but it's also a working farm. And so as I was putting my tripod up tonight, the local chickens came over to see what was going on. So apparently chickens also interested in astronomy. This is my setup tonight. This is what I'm working with and what we'll be showing some views for you of. I thought, given Amir's presentation, I would start with within our solar system, maybe move a little further out in the galaxy, and if we have time, move out to our closest neighbor. I will say we are very lucky. I've tried to do these a few times with Amy, and we've sort of struck out on weather. Tonight is actually beautiful, which is great, particularly because this week we had some clear nights. I'm going to show you this image. Surprisingly, this is from an app that I use to look at the sky conditions. I can see cloud cover, things like that, which is very important, obviously, for doing astronomy. But this was from Tuesday night, where it was supposed to be clear here in the DC area, and you could almost see nothing. I pulled up an app that actually, this shows smoke in the area, and you can see this purple, which is on the heavy side of smoke, all the way from where I am up here in Virginia, going all the way up north to our friends in Canada, and that was a result of the fires going on currently in Canada. So just amazing when you think how far that smoke traveled. Just very frightening, but I don't know, I thought that was somewhat interesting. So anyway, I have two telescopes set up. The one on the left, this white one over here, is my refractor telescope, which is mounted on an equatorial mount. And the other one I'm going to show some views of I have it currently on a planet, is my Schmidt-Cassegrain telescope. It's on a Alt-Az mount. So we'll start there with just a view of what I have right now. I'm currently trained on Saturn. It's not super centered at the moment. I guess I could fix that, but I'm going to leave it for now. Interestingly enough, it is clear, but as you look at this image, it doesn't look particularly stable, and that's a sign that the seeing tonight is not particularly good. And essentially, what's going on here is the atmosphere that we're looking through is not particularly stable tonight. It's a little windy out here, but on nights like this where the seeing isn't great, this is kind of what the planets look like. And even on the good nights, when seeing is pretty stable, it's still kind of, the planets tend to come in and out of focus. And the way to think about this is, it's a little like looking through, looking over a hot grill, for example, when you're outside and it's the air is disturbed and you're seeing that image kind of looking screwy behind it. That's what's going on right now with Saturn and the other planets tonight. So not a great night for planetary imaging, but I thought I would show you this particular image live. In preparation for this, though, I did take some pictures recently of some of the planets. I will say I'm not necessarily, my specialty isn't planetary imaging, but you can see this is a picture I took recently of Saturn that came out not too bad. You can see the Cassini division here, which is that black stripe that goes in the rings of Saturn, which is not bad. And actually, if you look at where I started with this, which was a video that we then broke down into individual frames, and have software that can pick out essentially the best frames, and you can build from that and sort of sharpen the image to get a good looking picture of Saturn. I also have one of Jupiter that I took recently that's not so bad. And I also have one here that I will share of Mars. Mars is a tricky one for me, but it's getting close to us right now, so this is actually a really good time to observe it. Last year's opposition of Mars, it was very disappointing for astronomers because Mars was in the middle of a dust storm, so some of these surface details just absolutely weren't available at the best time for Mars last year. So the guys who are really into planetary imaging, this is a great time of year for people to be going after Mars. If you happen to be on Facebook, you can look up some astronomy sites, and if you join some of those groups, and just do a search on astrophotography, astronomy, and certainly you will find lots of examples of this. You can join and see where astronomers and astrophotographers all over the world are post images to the site, similar to this, which is a lot of fun for me and for lots of others. Okay, so switching over right now to my refracting telescope, my refractor. This is images that are coming in live right now from the Eastern Veil Nebula. The Eastern Veil Nebula is the remnant of a supernova that star that went supernova somewhere between 8,000 and 10,000 years ago. This particular cloud that we're looking at is about roughly 2,000 light years from Earth. I guess I can't see it because I see you guys here. I don't know if I can hide you guys here. Let me see here. Yeah, I can do that. So as you're looking at my screen, it is black and white. The images that we take start in black and white. I'm using a filter right now. You can see here, its current filter is HA. It's a filter that filters out pretty much all light, but a very specific segment of the spectrum called hydrogen alpha. And this is the spectrum of light that's released when hydrogen gas gets ionized. And so you're looking at an image of that spectrum. These types of filters are great to use for filtering out things like light pollution. Fortunately, I'm in an area right now where the light pollution isn't particularly bad. So getting some good data coming in from this. Later on, when I've gathered lots of data, which typically takes 2-3 nights, depending on the image that I'm working on, I'll put that all together into a color image. I've been gathering data on this over a previous night. So this is not a completed image, but I thought I would show you what this looks like, what it will hopefully turn out to later. Image in process, but this is a picture of the Veil Nebula. You can see right now it's somewhat noisy. There's sort of lots of blue and red in there in the background. As I gather more data, some of that noise will disappear, but I thought at the very least, I would give you a look at what this image looks like, and hopefully it'll get a lot better as I keep working on it. So that is the Veil Nebula. The other thing I thought I would do, since it's a pretty nice time of year, is maybe switch over, and if we have time, switch over and take a look at the Andromeda Galaxy. And I thought if I change targets, you can get a sense for how this works. Is I've pre-selected, so the Andromeda Galaxy happens to be in the constellation Andromeda, shockingly. It's our closest galactic neighbor. It's about 2.5 million light years away. And so what I'm going to do is I'm going to center on that target. And what it's going to do is, you may hear it in the background. Let's see, where is it? You may hear it in the background. Well, my telescope will start moving. I know why. Sorry, guys. I have to stop taking pictures before I do that. So hold on one second. So let me abort that sequence right away. Okay, so some really cool parts of these tools. It's pausing right now. Apologies. And it's taking a long time. I don't know why. Okay, now we're good. Okay, so this move to and center on the Andromeda Galaxy. It's going to check, and you may hear it moving in the background. What's going on here is my telescope is taking a picture right now to see what it's pointing at currently. It's going to move to where it expects to find the Andromeda Galaxy. I don't know if you're hearing that beeping, but I certainly am. This is my guiding software. A little upset. Okay, so what it's done is it's moved over to roughly where it expects the Andromeda Galaxy to be. It's taking a picture. It's going to compare that against a database that is in my laptop against the whole sky. And it will say, okay, we're pointing in exactly the right place where you wanted it to point. I have it set within the 50 pixel limit. So we're 69 pixels away right now, which isn't terrible. So it's going to make a little move and take another picture, compare that against the database, and hopefully on this time, it will be right where we want it to be. And there it is. So you can see the error here is within 4 pixels. And so you can already see, and this is just with a 3-second picture. Whoops, sorry. Within a 3-second picture, you can already see this is sort of the heart of the Andromeda Galaxy, the center of it. So what I'll do just for giggles is take a quick picture. Maybe we'll do like 30 seconds and see what that looks like. We'll take one. So the camera right now isn't probably rotated perfectly in the exact right spot for Andromeda, but we'll take a 30-second image and we'll see what we get. I'm hoping that we'll be able to see some of the dust lanes and you know, some more definition to Andromeda than what we're seeing here. Andromeda is so big that I've previously imaged this. It's one of my favorite pictures that I've taken, but it was actually 2 images that I had to stitch together electronically. And you can see, maybe you can see it here, maybe that's difficult for you to see, but you can start to see some of those dust lanes appearing. Let me see if I can adjust that. Yeah, it's awfully tough to see with just a 30-second exposure. But you can start to see some of those spiral arms. For photos like this, again, this is long exposure photography. Typically, I'm taking images of Andromeda. That's probably a 2 to 3 minute exposure that I'm taking, and then later putting lots of those images together into one large file that really starts to show deep detail. And so this is a finished product of the Andromeda Galaxy that I've taken previously. It's one of my favorites for sure. This actually, I was fortunate enough that I submitted this to a magazine in the UK called Sky at Night, which is BBC publication, and this actually got published in that magazine, which I was very proud of. But that's the Andromeda Galaxy. So just a quick swing around the solar system here while you're here. An object, a supernova remnant within our own galaxy, and I thought I'd show you an image outside our galaxy as well. And I think that's all I had for you tonight from Sky Meadows Park.
Well, Brian, so before you're done, actually, I'd like to maybe have you, and we're about to go blank here because I didn't have my face on, my video on. So if you wouldn't mind talking to everyone, if you want to bring up the Andromeda Galaxy again for just a second and talk to everyone, if they were to walk outside right now in the dark, Arizona, don't walk outside, it's not dark enough. If people were to walk out in the dark tonight, and which direction? So of course I know the answer, the side know the answer.
And
But
you're hoping I do too.
if yeah, you're hoping you do. Look it up really fast. Just to be sure. We'll help you out. Daniel and I'll help you out.
I know where it is.
You forget. On the spot, sometimes it's hard. So if they were to walk out into the night right now, where should they look? What time is best? And basically, what are they looking for? Because when you image, of course, right now we see this beautiful image. You see the spiral arms. You actually can see some other galaxies doing some weird stuff. And then in the image pre-processing, of course, you just see the core and a little bit of that disk coming out. But if you are just a person with your eyes, it is visible.
Yes.
From Earth with the naked eye. What are you looking for and where are you looking?
Yeah. So, and that's a great question, Amy. Thank you. So, the thing about when you're looking at astrophotos like this, right? When you look through a telescope, and for those of you who have, that things like galaxies look nothing like this. They look what we call as a faint fuzzy. And so if you look at this galaxy that Amy mentioned down here at the bottom, in some ways, when you look through the eyepiece of a telescope, Andromeda would look something like that, is just this faint fuzzy. And the reason for that is that your eye just isn't nearly as sensitive as the camera is. And you're watching it in real time, whereas the camera is exposing the image for minutes at a time, if not longer, depending on how you set it up. So it will look like a smudge. So if you are in an area without a lot of light pollution, like I am right now, I will have a heck of a time seeing it because I have this bright white light in my face, so my night vision is terrible right now. But if you are familiar with the constellation Cassiopeia, which looks like a W, and it's up in the sort of northeastern part of the sky right now, it's kind of tilted on an angle. But if you look at the bottom point of the right side of the W of Cassiopeia and kind of come down there, probably about a fist width at arm's length from you will find kind of straight down the line of that towards the Andromeda galaxy, or the Andromeda constellation, which is sort of these three stars in a angled line, sort of. If you look there, and you'll have to sort of stare at it, and you might have to sort of look away from it just a little bit, use averted vision so that you can, it's a little easier for your eye to pick up on it if you're not looking right directly at it. You may see a smudge like this. You'll see this sort of ghostly area that almost looks like a bit of a cloud, which just is amazing to me that you've got this galaxy that's 2.5 million light years away and is so big that we can look up in the night sky and see it naked eye. So if you don't know where Cassiopeia is, if you don't know where Andromeda is, that's okay. There are some apps that you can download to your phone, both on iOS and on Google. Just look up for astronomy apps, and you can search for targets in there. You can hold your phone up and it'll use the compass built into your phone, hold it up to the sky, and it will give you a pretty decent idea of where to look. So if the instructions I gave you weren't clear enough, download one of those apps, follow the way there, and particularly if you live in an area that's dark enough without lots of light pollution, you should be able to see Andromeda all on your own in the night sky. Binoculars help a lot too. So if you have those, it doesn't take anything crazy. Go scan that part of the sky and you will certainly find it.
Great. Thanks so much, Brian. So I have one more question, one more thing.
Sure.
I would like you to bring up, if you don't mind going back to your photo of Jupiter.
Sure.
And just for anyone who's maybe a little bit unfamiliar with Jupiter as a planet, if you'll talk a little bit about the Great Red Spot or the Red Eye, and then we were talking a little bit in the chat too about the very tiny storm, in comparison, of course, the tiny storm that's brewing right there, right next to the Red Eye. And I actually myself can see it in the photo, just barely. I can barely see that. So if you don't mind talking about that just a little bit, if you can, I think that would be very interesting for everyone to hear about what's going on there.
Yeah, I'd be happy to. So this is, this is sort of the iconic version of Jupiter when that great red spot is pointing towards us. And I happen to be lucky the night that I took this, that it happened to be facing my camera. So as Jupiter rotates, sometimes it's pointing towards you, sometimes it's pointing away from you. So this night happened to work out great. So this is essentially that great red spot is a large storm on the surface of Jupiter, sort of. I mean, in the gassy area of Jupiter. It's essentially a giant storm that has been going on for, geez, I mean, as long as people have been seeing it. And so, but I do know, however, that great red spot over the years has been getting smaller. So, and it's hopefully it doesn't go away in our lifetime. It is, because it is certainly one of those great things to look at. You can see it through a telescope when you're looking. If you have a good night, you can definitely see that with your eye. You can obviously see it in photos as well. It is a huge storm. I mean, I want to say, I should have prepared for the same. I mean, it's bigger, I think, than the Earth. I mean, this is a huge. This is a gas giant. That is a huge storm, and it's just been in that same spot for, geez, I don't know, hundreds of years. I would imagine.
All right. Well, great. Thank you so much, Brian. I know that
You're
it's
welcome.
probably super cold there. Every time we have engaged you, it's been the late or the middle of the night out there in Virginia, and I know that it's cold, and I really appreciate you going out there and doing that. I hope it's not quite into the low 50s or 40s yet.
It's not so bad tonight. Winter's coming. That's when it gets really interesting.
I only see you in a hoodie, so that's good in comparison to where we've had you before. So
True.
I think everybody really appreciates you being here tonight, and this was incredible. Thank you so much for sharing your Andromeda photo. And the one last thing I'd actually like to talk to you about before we head over to Daniel is,
Yeah.
You mentioned dark sky adaptation. So the way that you're viewing, because you have that white light in your face.
Yes.
If you can just talk to everyone for just a second about how that changes your vision, because light pollution is such a big deal in so many places, and that white light really keeps us from seeing the night sky and really enjoying the stars and connecting with them.
It really does. And dark sky is it's tough to find these days, particularly on the East Coast. There are just so many cities, so much building, so many lights everywhere. It can be very tricky. I've done some public outreach nights in Washington, D.C. itself, actually downtown, like in the shadow of the Washington Monument. It's difficult just to find stars to align your telescope to when you're downtown. And there are plenty of people in the country who have never seen the Milky Way. If I turn and look out here tonight, I can see the Milky Way in the sky, and that's not everyone has been able to see that. And so, to be able to get out to a place where it's dark and see the sky, see the stars sort of, in all their brilliance, if you haven't done so, it's totally worth it. It's very important, as Amy mentioned. White light is not the best thing for your eyes. So certainly, everyone's experiences driving down the road at night and then a car goes by with high beams on, et cetera. It takes a while for your eye to really recover and get your real adapted night vision. Can be lots of minutes. And so I'm fortunate I'm the only one out here tonight, because this white light would not be appreciated by my fellow astronomers, because it really affects your ability to see things. So I was looking up to look for Andromeda while we were talking, and I can sort of barely see Cassiopeia just because of this white light in my face. So if you are going out and trying to find something, or are going out, turn off the lights outside, and it'll at least help you. And if you can't see things right away, stay out there for a while and just as your eyes adapt, you will be able to see more and more of what's lighting up the night sky. And I encourage you to do that, because it's become an absolute passion of mine to be out here. It's one of my favorite places to be, out under the stars when it's quiet, nobody else is around. It's it's just an outstanding hobby.
Well, great. Thank you again so much, Brian, for being
My
here.
pleasure. Thanks for having me.
And yeah, you can go ahead and turn off that light so you can see Andromeda.
All right. See ya.
Bye. All right. And everyone, thank you so much for sticking it out with us. We have one more astronomer tonight, one more star presenter, and here with us tonight is Daniel Cervantes from Bloomington, Indiana, and the Feynman Observatory. And he has some pretty exciting things to show us as well. So without further ado, I'm going to go ahead and turn it right over to Daniel, and he will help us finish out the night.
We're able to show so much, because I'm running a little bit behind. It's so far it's been a clear night. Tonight we were going to try and look at NGC 6543, or for some of you that are more familiar with it, it's called the Cat's Eye Nebula. And my cat just decided to come up here. It was sort of, I guess, done for her. But anyways, I'm running a little late, but that's fine, because it's going to be a long night. And I thought what I would do is I'm going to go ahead and turn my video off and share my computer desk here, because I've got multiple screens here. I happen to have an observatory that's in the backyard, and it's a roll-off roof. So I actually have an operating room here in the house. So that's why I'm indoors right now. So lucky, after all the years of going outside, it's much nicer to be able to just come in the house and operate everything from in here. But I'm still in the process of just finishing up on getting focus points. So what I'm going to do is I'm going to kind of take you through the process of where I'm at now. And I think we can go ahead and start bringing up the object we want to look at. And I'll take you through the process. So hopefully you'll find that interesting. And I'll kind of explain sort of what happens with each of these steps. And then hopefully we'll be able to get a short image. It may not be a real good one, because we can't take real long images, but I can put the gain up, and we hopefully can get a couple good images through a couple of the unique filters. So Amy, have you shared it to me? I don't see anything here.
Control.
Okay, here we go. Okay, share screen. I'm going to try and share my, let's see if I give you the right screen. I need this one. It's blank right now, but I'm going to switch over here in a second. So, and let me turn my camera off first. I'll feel more comfortable that way, because I'm going to be jumping all around. So I may not be able to look into the camera. But I'll keep talking to you, and let me know if you see this over here. Do you see where the arrow's moving around over here? Is that showing up for you?
Yes, we see that now.
Okay, here's where I'm at right now. Like I just said, we were going to try and look at planetary nebula tonight, which is basically what happens to most stars when they die. They sort of throw off a lot of gas, and the gas that's out, that's thrown off the normal lifetime of a star, you sort of get these two forms of gas that eventually will compress into one another. And depending on the age of the planetary nebula, you'll get them to look in sort of slightly different forms, because they really only last for just a few thousand years at most. So based on which one you're looking at, they'll all look slightly different, but they're all really fairly cool looking. So where we're at right now is, like I said, the first thing that's most important is focus. You have to have good focus, especially when you're taking long exposures. So I'm in the process right now of doing kind of the last of the focusing. And right now what I'm doing is I'm going to go ahead and just show you one or two focuses that I'll take just to show you how it works. But I'll take one through H alpha and then another one through our O3 filter, and I'll talk about those after I do that. But basically, we have a routine here where you could, once you get something that you can go ahead and try to focus on, this thing will do all the focusing for you. And you collect a bunch of these numbers. So you'll see here, this one is starting out right now. It's telling you what the temperature is, because cameras basically, they vary with temperature, the focus, because the telescope is obviously getting warm or cold, so it's expanding or contracting. And so your focus actually changes as the temperature changes. So by going through this, if you see this little thing over here, this is where these things are going to go, and it'll make a chart, and it'll calculate basically how much your focus changes per degree. So the hardest part is to get these for H alpha. For some reason, that's the hardest one to focus. And the skies are fairly good tonight, so I haven't had any bad luck yet. And it's, even though it's been clear the last week, like Brian said, smoke is killing Indiana. I mean, you couldn't even hardly see the stars at all where I'm at, even though it was supposed to be clear. But tonight, it appears to be breaking up a bit because I'm getting fairly good focusing. So basically what you do, you go through, you get a whole bunch of these focus points, so you know the temperature and the actual position. This is an electronic focuser, so the computer's driving it and it's saying, okay, here's where we're at, and this is just a number that goes from 0 to 64,000, and will tell you where it is based upon the temperature. So we know what it started at, what temperature it was. We now know its position. We'll just go ahead and do one more just so you can sort of see. We'll go ahead and do it. H alpha, let's go ahead and do it with the one that I'll probably do the imaging with tonight, O3. I'll be doing more later, but for the 12 minutes or so that I've got, I'll be able to show you here. So basically, I'm going to go ahead and let the electronic filter will rotate and put the filters, the one that you want, right in front of the camera. So, and this program here will actually work with another program over here to tell it to move the filters. So basically, we're going to go ahead and just do one more focus for O3. And it'll tell you again, 12.8 degrees it's starting at. And we hopefully will get a good focus here. And actually, I probably shouldn't be talking and focusing because I need to. I don't want to use the whole image. I'll use a subframe. So there we go. There's the subframe. And we'll start that again. So it's going to go ahead and start focusing. It's approximately 12.8 degrees Celsius right now. It'll go through, and so basically what I've been doing for the last, well, I don't know, hour and a half or so, because I'm starting a whole new list of focus points. You can actually keep these and reuse them, but you have to do a few focuses just to make sure it knows where it's at before it'll accept it and allow you to use the entire collection of points. And there's reasons why you have to do that, because things will change based upon the air and different things. So, but basically, hopefully we'll get here. This is the first time I'm seeing one's not going real well, it doesn't look like, but I think it'll come out. It may just have moved since last time I did a focus. So looks like the focus is going to be on this one back towards 22.6. And then once we get this done here, you'll see, I'll just go ahead and close this out because this will take just another minute or so here to finish this one focus point. Hopefully it's a good one. Normally I would do a bunch of them at each temperature, but just to sort of speed things up, it won't hurt. I can come back later after the presentation and go ahead and do some more. But for now, just to kind of get us a good graph here, and this will finish here in just a second. So basically what it's doing is you got to tell it a little bit about your focuser. In other words, how far does it move and what's your focus range on your focuser. and it'll calculate these different positions, and it does basically 2 on each side. It does what it thinks are 2 on each side, and then it'll draw the actual slope here, and it knows approximately where the best focus is from that. And you can see the ones that are the higher are the better focus points. So it'll calculate that for you, and then it'll give you the point you need, and stick it on the graph, and then you'll see here. Just a second. I should know that this is the one that decided to go slow on me here. But this is actually nice. So once I just reconfigured the whole telescope, so I don't have a lot of old focus data. So I had to really get a lot of points measured tonight. Okay, so we get one at 23,206. So we'll just assume, okay, that's enough for the moment. We'll go ahead and get out of this autofocus section. We'll tell it to go ahead and use the values that I've given you tonight so far. Calculate all your slopes, and there's offsets. In other words, the focusing for each one of these filters will be slightly different because not all filters are perfect. And then I'll go ahead and save it so I don't lose it. I've done that a few times this week. Luckily, though, it wasn't very good, the weather, so I don't think I really had good focus data anyways. Okay, so I'm going to go ahead and tell it now to activate focus. And so now it's going to focus on its own. So it'll know what filter, if I can get this thing from jumping around here. Okay, so I activated the focuser now. So now it's going to look at it gets the temperature from the actual focuser itself. There's a focuser temperature on here, so it knows what it is. So it'll go ahead and try and draw down this line. I don't like the way this presents this very well because you don't see that they're changing, because for some reason this y-axis, I don't know how to adjust it yet to see it, but I don't really need to see it. But so basically we activated it. It's going to focus on its own. So what we're going to do now, and I don't know if I don't think you'll be able to see this screen, but I'm going to go ahead and move the telescope to the object that we need, because I was focusing on a couple of stars. And then I'm going to go ahead and tell it to, let me see if I can move this over so you can see it. It's not really that interesting, but I will. Here's my little camera window. It's on the other display. Too many things on one display are the most difficult thing for me. I have to have 2 displays, so. But we'll go ahead. I told it to move already, and it's probably sitting pretty close where it needs to be. We will go ahead and change the filter so we can find it, because we have to find a guide star, and I'll take you through that here in a second. So we're going to move the filter to the luminance filter. This basically allows most all the light to come through. It just filters out some ultraviolet and infrared that you don't want on your cameras. That's really all this luminance is for. It's also used when you produce the images. It gives you sort of brightness data of the object, and then you'll use your color images to give you the color. We'll see what happens here when I start taking photos. Probably not going to be enough to see anything yet. Hopefully we're close. I'm kind of zoomed in, so let's do this. Turn the subframe off so we get the whole camera image. And then we'll add a little time to it. We'll see if we can find our object we're looking for. Ah, there we go. This is it here. Unlike Brian, I have to do mine manually. So we're going to go ahead and move that guy to about the center of the camera, because we're going to image with just a subframe. We're not going to use the whole frame. This is a relatively small object. What we're doing here, and the reason why I have to go through all this auto guiding on this one in particular, is because we're looking at pretty high magnification on this. We actually have a 300 millimeter Mac. And what's unique about Macs, they're not very popular telescopes, are that they basically are f/15, which basically just means that it's high magnification is what it means. But that means that there's less concentrated light coming in because you're blowing it up so much. So once we get this thing here in the center, and we could probably take that down a little bit to speed things up here. Come on. I hope, so we can see it. Okay, here's our subframe. So we're taking basically just 1/4 of the camera's imager. We'll try to get it approximately centered. And if I remember correctly, I think I want to have it a little to the left, because the next step is the most difficult part of this for me personally. Everybody has their own thing that's, you know, way they do things. But for me, to get this guy right where you want it, because even though this thing tracks very well, the problem is not any mountain telescope is perfect. So what you want to be able to do is to be able to find a star, and you're not going to see it here within the field of view of the imager here. We're going to pick a star out of here, and there's a second camera that's offset from this camera, and we're going to spin it around. So we're going to start by spinning the camera around here. We've got a camera rotator right here, and I believe there may be something at about, and this is purely based on memory, I may be wrong, at about 109 degrees. So we're actually spinning the camera. So you'll see it, yeah, I didn't spin it very much, but I did a little bit. So we're going to go ahead and see if we can get this back to the left just a little bit. Everything's now offset because I moved it actually 19 degrees. It's set right now at 90 degrees. It goes exactly east and west, left and right, and north and south, up and down. So come on, let's go up just a little bit. Okay, I think that, okay, that should be good enough. Okay, now we're going to try and bring up the auto guider here. I'm going to get this out of the way because it'll make it easy. You won't be able to see that, but this is just the camera control. We're going to bring up the auto guider.
Daniel,
Yes.
we have a question for you while you're doing that.
Sure. Yep. Go ahead. It's easy to.
Yeah.
I can answer as we're going.
Right. Have you observed any interference from the SpaceX?
You know, I haven't. You know what? I don't really know because I've just started. Really, I went from just observing planets to starting to do a little deep sky stuff this last year. So I really don't know how often you see satellites come through. I've seen a few come through, but I think that's kind of normal. So I don't know if it's because I'm not looking in that particular part of the sky, because I don't really know how they're patterned. I guess they're going all the way around, but I haven't noticed them yet. But again, I'm just starting out with this, so it's hard to say. I know a lot of people are upset about them though, and I don't blame them.
We have definitely seen them in Arizona. They're very,
Yes.
very noticeable. You would know. If you saw them, you would know what they were.
Well, but you see them right after they launch them, right? Because I know that you don't see them after they get up to altitude, I don't believe. I mean, maybe you do through the telescope, but you don't see them like you do here, where there's a big train going through the sky. That's just as they're moving up to their final orbit.
Yeah, so we see the train at first, but definitely through telescopes. Yeah, we occasionally will get multiple lines. People are getting multiple lines through their imaging.
Yeah.
Lately, so
I haven't suffered from it yet, but again, I'm just getting started. I finally got everything working really to be able to do. I've just been doing more testing the last 6 months, and now that everything's together. So I haven't really noticed yet, but yes, it is a problem. I do know that. Okay, so here's our auto guider here, and what we're going to try and do now is there's a kind of a setup part, and we're just going to go to this focus tool, and really all that's doing is just going to take images for you, so you can kind of see what the focusing camera sees. So there should be another thing plops up here somewhere, and I don't see it. Ah, here it is. Ah, here we go. So there was that bright guy right here that I was hoping I would find. So I think that's going to be a good guide star, and it tells you here exactly, it's saying a maximum of about 36,000, which is pretty good number. So it's a nice bright star. So we're going to try and tell this auto guider now, we're going to calibrate the auto guider. So it knows exactly when it sends commands to the mount, which way the telescope's moving. You got to remember, I got a rotator on here. So this changes every time you turn the camera. It also turns the guide camera. So it has to calibrate this. Hopefully all these parameters are set up, and I'm going to go through this kind of quick just for the demo, but I hope that they're all set up okay. I think we can just go ahead and tell it to calibrate now, and hopefully it'll calibrate successfully. Let's see. I'm in auto guide. Why is my calibrate now? Oh, wait a minute, I was still taking pictures. Okay, here we go. Okay, so it'll take one more picture, then I can calibrate it. Okay, so let's try and calibrate it and see what happens here. And I'll tell it to use this. I probably should have hit the auto find, but it doesn't work either way. So what it's going to do right now, and you'll see this thing, it's a little bit hard to see on this display, but basically you're going to see the star move in sort of right angles to one another. And you can't see it here. There's some little green lines here saying, yep, it moved this way, and then it's going to move back, and then it's going to move at a right angle, and then back. And then it's going to use those numbers by knowing how long it told the mount to move in both dimensions, how far it'll actually move it. So when we get done with this in just a second, it'll be done here in just a second. I don't know if you're going to see the window. It may pop up on my other window, but it's just going to tell me it says it was successful. So I'm hitting OK. And then I'm going to go ahead and say, OK, go ahead and start auto guiding. So hopefully now we can watch these numbers right here and see. Right now it's saying it's off by 15 pixels and off by 2. And that's normal when it first starts up, because there's a little delay between you hitting it starting and the thing moving. But it usually should kind of settle down. You can see it here right now. It seems to be, these numbers are supposed to be like less than 2 each. So because I have very small pixels on my camera too, my pixels only have about 1/10 of an arc second, because I'm shooting at high magnification. So for me to be able to maintain these low numbers is very good. So the accuracy of the mount is very good. I'm going to get this out of the way because we don't really, you don't need to, well, let me explain this to you first. Why we're doing this is it's taking pictures of this every 6 seconds, and it's comparing where this star was to where it was last time. Now this image isn't updating because I tell it not to update because it's just burning up more processing. But basically you would see this star bouncing around just a little bit. And what it does, it measures how far away from where it was before, and now it knows to move it. Let's say it bounced in this direction. It would know I got to push it back to here. So it knows where it was originally and it keeps it there. So that's why the camera won't drift. So if you've got a good mount, and you can see it right here, it's going to move around just a little bit, but most of that moving here is just due to the atmosphere. It's not really due to the object moving. So that's where most of this is at, because this is really, well, that one went over 1. That's not good. Come on. Hope it didn't go off the screen. Well, wouldn't you know it? We seem to have trouble in one dimension right now. So something's, yeah, let's abort this and do it again. You have to be a little careful on this. What I say is what's difficult about this is these stars can't be too near the edge of the camera, because it has to look at, and I have everything set, right? I've got all, I think I set everything okay. And we'll try and calibrate it again. Okay. I don't know why it did that. It looked like it was on the right thing. And I had a good calibration. So maybe we do have a little bit of haze going on up there. But anyways, once this thing gets calibrated and it starts tracking, and we get the auto guider working here. But there's a lot of parameters you have to set up when you get an auto guider. So that's where you're gonna have to read a lot about auto guiders if you ever get one, because you have to know exactly how far these things move, how the camera rotates and determines the axis of your north, south, east, west on your camera, and up, down. And you have to learn a little bit about how far you want it to actually move, because sometimes you don't want it to be too aggressive. See, right there, it was getting close to the edge, but it says it's got a good calibration here. So I don't really know what, maybe I didn't click it quick enough. Now let's see here. We'll watch it again, see if this settles down here. I don't think it's moving off. Get this out of the way. Well, I'm going to assume that it's settled down. So we'll just go ahead and get to the next step. So this thing is guiding now. So we'll just move the auto guider out of the way. Normally you got to watch it to make sure it doesn't go, it gets, I like to keep it under 1. And I've been able to lately to get it to where the parameters are set that it's tracking pretty good. And it's still there. Okay, so now we'll get back to our camera again here. And we will now start imaging. So we'll start out by doing, let's do the, why did it switch cameras on me here? This is auto guider. Okay, here we go. Okay, so what we're going to do now is we're going to go ahead and let's just go ahead and start shooting. I'm just going to shoot all these frames for now. I don't know how they'll come out, but we'll start out and you'll see we've got we're going to take a whole series of images here. So we're going to take 20 of them through the O3 filter. Let me move that now just to get it out of the way. Sometimes the camera shakes. There should be a delay factor in here, and for some reason it doesn't seem to be working. I can't get it. It should be delaying between each one of these runs, and I don't know why. And the filter moving, the filter wheel when it moves, because this thing knows to move it to the O3 filter. Well, usually the first image after that isn't always very good, especially on a short image. But basically, it's going to take 20 of them, and it's going to repeat it 20 seconds, and it's going to repeat it 10 times. Then we're going to take 20 second images through hydrogen alpha, 10 of them, and then also through blue and through luminance. And we're going to combine all these into an image, which unfortunately I probably won't be able to show you tonight because I think this is going to take up about 12 minutes, this run. But I just need to set up one more thing here. Everything's set up. I need to tell it to where I want the images to go because I don't think I set those yet. So I need to set up the autosave function, and I've already got it set, so that's good. And it's stable, so it's tracking good. So we'll see, and you'll see the images update here. So we're going to go ahead, and it looks like hopefully we'll have a good run here. And we will take the series. Yes, leave the subframe on. Okay, so you'll see it here. So the first one, let's see if you can see it here. It's telling you right now it's exposing it for 20 seconds, the first one. So it's actually, you see the O3 filters there. And if you can stand to stay around for 10 of these at 20 seconds each. you'll see this thing count down, the number of images count down, and then you'll see it actually move the filter. I use the sky, and what's nice about the sky, ooh, you know what? It's overexposed. Oh, that's not good. You know what? I hadn't shot this and I had guessed as to what it's going to be. So we're going to abort it, and I'm going to have to do a little less than that. Let's try 15. I normally don't shoot. This is at high gain, which basically means you don't have to shoot as long, but they're noise or images. But I thought for the demo, I would try using, and I'll go ahead and set this to be the same. Just I know that the hydrogen alpha isn't going to give us much of a. Okay, so the auto guider here is still working. So that's going to start again. And we're doing good here. So it's tracking well. So it's going to try 15 seconds. Anyways, by turning the gain up on the camera to shorten the exposure time, you throw a lot of noise into it, it's still, wow, I miscalculated that completely. Because normally I'm shooting these at multiple minute exposures.
Well, and that's okay, Daniel. You know, we're running a little bit short on time and a little bit over time. But is there anything else you'd like to show?
Yeah, I'll just go ahead. Yeah, let me just kind of tell you what I need to test these anyways. Yeah, so what happens is basically now we're going to end up with 4 different color images. So you have this luminance, which is just basically a black and white image. And then you're going to end up with this, or I'm sorry, this isn't the luminance, this is the O3. O3 is going to measure oxygen too. So it's basically the two gases that I was telling you about inside a planetary nebula are the oxygen and hydrogen alpha. Hydrogen it's got 1 electron that's bumped up into its higher orbit. Those are the 2 primary gases you're going to see in planetary nebula. O3 is definitely the number 1. H alpha, some of them aren't quite as strong in that based upon how old it is. And then the other one is just blue, because when we make this image, O3 actually is in the green. So we're going to make it green. We're going to take hydrogen alpha, which is red, because this is the same filter you use to look at a solar eclipse around the edge of the sun, where you see that little red chromosphere around the sun, if you've ever looked at the sun during the eclipse. And then blue, so it kind of gives you something of realistic colors, but it really gives you the scientific data in these 2 primarily. The blue is there because it really shows off the bright star in the center of the planetary nebula, because it's a very hot, usually very hot stars. And then the luminance just gives you sort of the brightness overall. And you can when you do your images, you basically have an option to say how much of this luminance do you really want. You can set it up to 100%, which basically means that's going to determine the entire brightness of the image. This will just add color. And then if you turn it down a little bit, the amount of signal you got from these 3 will actually impact the brightness of each section. So I'm trying to think what else. Other than that, really, that's it. So the big thing with deep sky imaging, focusing is critical. If you've got the tools, I'm lucky. I've got, I've worked, I'm retired. I've got electronic focuser. I've got all the software that talks to the focuser, talks to the camera, and all these software components all talk to each other. So they pass all that information around. And then I'll just show you the last thing, I guess. Here's what's in a normal astronomical image.
Well, I think maybe Daniel, do you happen to have a processed image? Nebula.
I could probably, let me see. I could probably, I'll just pull one up. Sure.
What all this work heads to.
Sure, yes. Oh, yeah, no, sure, of course. Yeah, I think I've really only done one object since I finally got everything working. And that one came out pretty good. I was pretty happy with it. And I just have to translate in my brain, what is the Ring Nebula? NGC, what's NGC on the ring? Can you translate that? Anybody for me real quick?
You're testing all of us for for our.
I know. Well, that's okay. I'm not good with names and numbers. I'll be honest. I mean, I'm good with calculating numbers, but
6720.
yes. Okay. Where's it at? Oh, so it was there. Okay. So I just have to figure out where it's at here. Here's our reduced images. So you got to go through a whole alignment thing, but you need more than 12 minutes to talk about that. I just got to figure out where I put it, which one of these things under here it's in. This is just, I'll actually show you just one of them. This is the, I can't do that here. Yes, I can. This is the blue. So basically when you combine all the blues together, this is what I've got. So you can kind of see what just one of them looks like. And then I'm going to show you what the final is. So, and you're going to get 4 images that sort of look like that, but they're going to show different things. The blue is showing, here is the star in the center, the hot star. So blue is going to show that. And then when you take the other 3 images and combine them together, okay, where is it at here? Probably an 03 or Loom. No, there's the 03. It's not there. Okay, at the end of it, it's going to be in the last place you look. It always happens that way. I'm not sure why, but okay. L fit. Do we see something that says RLG? It should be. Here we go. So I'll bring this over here. Come on. It's showing up on other display, but it'll, for some reason on my laptop, it doesn't like to show JPEG images very well. It takes forever for it to bring one up, and I don't know why. I guess I could just open up let's do that. It'll be easier. Let's get out of this. I'll open up the actual scientific file. And here we go. So this is kind of what happens when you combine all those together. So you can see the green here in the center, that's concentrated where the O3 is. So that's where the oxygen is concentrated in the center. And then around the outside, you're going to see all of this hydrogen gas. And then the blue just kind of combines, shows you a lot of the hot stars mostly. That's what you're going to see all around here, hot stars. So that's what it all leads to. And I'm having a lot of fun with it. And if you're ever interested, I didn't talk a lot about myself, but since we're running late, I can just tell you, if you want to look for Feynman Observatory on Facebook, we've got our own page there, and that's where I'll put all this stuff that I get done with, including hopefully what we get done tonight, if any of these come out. And I've already, no, here it is. Oh, last thing I was going to show you this real quick. Inside these files, for those of you that are into astronomy, when you get to the astronomical cameras, these FITS format, and that's how it keeps these images. So they're not like JPEGs or BMPs or anything. It has a header on it, and it has a lot of information in there. It tells you how many pixels in the camera, and who you are, and where it was taken, the kind of cameras in it, all kinds of stuff. Temperature, not only the temperature you set it to work at, but the actual temperature of the CCD, tells you temperature from the focusers, tells you what filter you got. It even, if you've got the right software and equipment, it gets from the mount the information, so it knows exactly where it's pointing, so it can tell you what the object is. So you can get all kinds of information out of this thing. So it knows, all the information you want to know, even tells you the focuser position. So there's a lot of information inside there that are useful to you. And other than that, I want to thank you for coming, and I'm glad I had a chance to show you kind of what I'm doing here. And I'm going to go ahead and I gotta shut this down to get back to my desktop. Oh,
No
can you
problem.
I don't need to do that, do I? You can take it back yourself.
No, yeah, I'm going to go ahead and I'm just going to take over. I'm actually going to show
Okay.
you one. So for many of you, you may be familiar with the NASA and Hubble images. And so what we're seeing tonight, there are lots of different ways to image night sky objects through different filters. We can look at them through hydrogen filters. We can look at them through oxygen filters. We have spectroscopic instruments. This particular image you're looking at is the same object. It's the Ring Nebula. It looks an awful lot like an eye. You'll see us talk about this again later in October because it's a little creepy looking, so it's great for Halloween. But this particular image was taken by the ESA, the European Space Agency, and the Hubble telescope. And so this is just yet another way to image and really look at what's out there in the night sky. And so I just want to say very last, thank you everybody for joining us tonight. And what's great about star parties like this in a virtual sense is that we get the opportunity to learn how many different types of telescopes work and how different types of science work. So we had the opportunity to see Brian's telescope working and showing us in real time what was going on, and then seeing how Daniel's telescope is quite a lot more like some of our very big research telescopes like the MMT, that a significant amount of work and very careful handling goes into slewing those telescopes or moving them, tracking those objects, and then bringing those images into focus, just due to their size and their functionality. And so a lot of effort goes into that, but we always have this very beautiful result at the end. And for those of you who didn't see the chat, what I had to say there, if you do live in Green Valley or Sarita in December, go ahead and keep an eye out for the Discovery pullout in the local newspaper, the Sarita Sun or the Green Valley News, and you'll see some of the images that our astronomers have painstakingly taken over many hours, so that you can see some of these beautiful things like the Ring Nebula from the Hubble Space Telescope, but taken at the MMT using our different instruments there. We're also working on a new project right now to take new images of different night sky objects there at the MMT. So thank you again so much for joining us tonight for the Star Party. Our next Star Party is on October 16th, and we will be welcoming Dr. Shane Larson from Sierra. That's CIERA. He's a very good friend of mine. And again, thank you so much to Amir for speaking to us about theoretical physics and the work that you have been doing. Thank you so much, Brian. And thank you so much, Daniel. And again, thank you everyone who joined us tonight. We'll see you again in October. Bye.